now?
Yes, we are.
All right. So welcome to today's seminar on the inspection and condition assessment of concrete structures, including service life evaluation. For those of you who I haven't had to meet yet, my name is Kieran Smith. I'm the Business Development Manager for Fraser-Nae, New South Wales, and I'm the current Vice President of ACRA. As we move through the webinar, if anyone has any questions during the presentation, there's a Q&A tab at the bottom of the screen, and we'll try to answer those questions as soon as we get the opportunity. Today's presentation is about the premature deterioration of concrete structures exposed to various aggressive environmental conditions, which has become a worldwide problem due to the excessive cost, environmental impacts, and safety issues. Structures need to be visually inspected and quantitatively assessed in order to plan the appropriate maintenance and repair operations. In order to propose the proper repair strategies and methodologies for both repair methods and materials, the condition of the structures must be assessed precisely. Any structural and durability assessments of the structures must include the following activities: detailed visual inspections, monitoring and measurement of quantitative parameters, data analysis, estimating residual service life of the structures utilising mathematical models, and providing optimised repair and rehabilitation solutions to extend the service life of any structure. Our presenter for today is Dr. Farhad Nabavi from Technocrete Structural and Durability Consulting Engineers. Dr. Nabavi is a highly motivated, passionate and professional civil and structural engineer possessing a PhD in structural engineering with a specialty in durability design and service life modelling from the University of Technology in Sydney. He has more than 20 years experience in design, construction, assessment and repair design of structures and infrastructure. He has published more than 25 journal and national and international conference papers related to concrete durability performance, design and modelling, and is the Managing Director of Technocrete Consulting Engineers. He is also a visiting fellow at Western Sydney University and an honorary fellow at the University of Technology in Sydney. Without further ado, over to you, Farhad.
Good morning, everybody. Hope you are all well in this situation. Today, I'm gonna talk about the inspection, condition assessment, and how we can model and estimate the residual service life of the structure and a bit of the repair strategy and strengthening. It will be through a case study. We know that the concrete structures and infrastructures experience various detrimental environmental conditions during their service life, like high humidity, temperature, wetting drying cycles, chemical attacks, physical processes. All of these will result in premature deterioration of the concrete structure. What does it mean? It means that the actual service life of the structure is less than the design service life. Then consequences of this deterioration is like excessive growing cost because of the highly cost of operations for the repair of the structures, environmental impact, the demolition of the structure, using material, using resources, power, and carbon dioxide emission more to the environment. Then safety issues, we will review this a little bit later. Very brief about the deterioration mechanisms in concrete structures. We have three main mechanisms. Chloride-induced corrosion and carbonation-induced corrosion, they are categorized as electrochemical processes because both of those mechanisms will result in the corrosion of steel reinforcement. And then the outcome is the expansion of the reinforcement, cracking, spalling of the concrete, strength reduction, section loss, and strength reduction. I mean, this is for both steel and concrete. It starts with the steel reinforcement corrosion and reduction of the diameter, and then concrete as like consequences of spalling. We can have like internal expansion, like sulfate attack and AAR or ASR. They cause the internal expansion of the concrete material. Or the solution of cement matrix. We can see this in the acid attack environment or soft water attack. Then both of them are categorized as chemical reactions or chemical attacks. And we may have internal inspection, which is with physical, like freezing, or we can have mechanical deterioration, like abrasion, natural sandblasting, waves, and debris. Natural sandblasting means if the structures are close to the coastal area in windy times, we have the like sands facing to the structure and do the blasting of the structure. Both of them are categorized as physical processes. Then chemical reactions and physical process, they are both attack on the concrete matrix. Then we will have degradation of the concrete matrix, mass loss, and strength reduction. All of these deterioration mechanisms, they can be classified as durability problem, but at the end, they will be converted to the structural performance and reduction of the structural strengthening of the structure. That's why when we say durability problem, then in long term, it can be converted to the structural problem. For example, I'm presenting some of the collapse of the bridges and a car park due to deterioration of materials, and they can be classified as durability problem, but as you can see, they are a structural problem at the end. The left-hand side, we can see the Morandi Bridge in Italy, 2018 collapsed due to corrosion of strands in pier number 9 and 10, and 43 people dead with 51 years of service life, and design life has been 50 years. The second one is a car park in UK, and we had like carbonation induced corrosion, and then due to reduction of the steel reinforcement diameter, we had punching shear failure. Then, as I mentioned, the durability problem has been resulted into a structural problem. And the next one is a pedestrian bridges only with 5 years of age due to corrosion of a steel reinforcement. And the right-hand side is a bridge in Canada, and after 36 years collapsed due to corrosion of a steel reinforcement, 5 people dead and 6 injured. But design life has been 70 years. Then look at this picture and the other collapse. I mean, in the other infrastructures like dams and water tanks and the other structures, it gives us a like idea that durability design and durability performance and planning is important as important as the structural design. When we are designing a structure, we have to provide a package of a structural design and durability design. Otherwise, we will face with the premature deterioration if we can only stress or focus on the structural design and based on the standard which we have. Now, our standards are mostly like prescriptive based standard, and we cannot rely on the outcome of those standard parameters if we consider them for the durability performance of the structure in that environment. Then for the concept of service life modeling, you may have seen this one. It's like after TOTI 1984, we have the degree of deterioration as the vertical axis and exposure time to the environmental exposure, based on year. Let's say we have chloride environment, we have chloride diffusion, then what will happen after some time? We have corrosion initiation time or depassivation of the steel reinforcement. We have, after some time, we will have the first crack or crack formation on the concrete cover. Then what will happen after that? We have accelerated chloride ingress into the concrete, and then we have steeper slope of the deterioration, and then spalling can occur. And then after that, accelerated deterioration and then collapse of the structure. The main focus of all research and effort on concrete technology is the increasing the corrosion initiation time. We try to increase the corrosion initiation time in order to increase the service life of the structure. For example, we work on the different materials, different additives, admixtures, coating systems to increase the corrosion initiation time in order to have like longer longer service life. Why? Because the corrosion propagation time is a very complex phenomenon, is a very complex process. There are different types of parameters and factors affecting the corrosion propagation time. And that's why we try to increase the corrosion initiation time in order to have like more healthy structure. For the durability modeling and design, as I mentioned, we have to focus on design stage for the durability modeling. Let's say a design service life of 100 to 200 years of service life. Then in this flow chart, you will see that we have to focus on the performance of the concrete structures and concrete itself, rather than going to the prescriptive criteria. Then what are the main factors which we have to consider in durability modeling as the microenvironmental exposure condition? First is the dominant factor of deterioration. For example, if the structure is exposed to the seawater or ocean, okay, the chloride attack, chloride diffusion is the main dominant factor of deterioration. And if it's in the like sulfate soil environment, then sulfate attack is the dominant factor. However, in reality, in real environmental exposure, it's not only one element attacks to the concrete. For example, even in sea or in seawater or ocean, we may have two types of attack on concrete. First is the chloride. Yeah, chloride is the dominant one, but the second one is the sulfate attack, like magnesium and sodium sulfate attack to the concrete. Then we have second dominant factor of deterioration. In our modeling, we have to consider the effect of the second dominant factor on the first dominant factor of concrete, of the deterioration when we are modeling the service life of the structure. Let's have an example. We have chloride attack into the concrete, and we have sulfate attack as well, two different mechanisms. Then what will happen? Sulfate attack will provide some expansion inside the matrix of the concrete. And after some time, we have some cracks, which those cracks can accelerate the diffusion and ingress of the chloride into the concrete, compared to the environment which we have only chloride environment, not the sulfate, then we have to consider at least two factors if required. Then temperature, relative humidity, and drying and wetting and drying cycles are the other factors which we have to consider as the microenvironmental exposure condition for that specific structure. After these, we have to model the mass transfer of those material or those elements into the concrete. And at the end of our modeling, we will achieve some numbers which gave us the like parameters of the performance of that concrete in that environment. For example, we achieve a number of like chloride diffusion coefficient. This number has to achieve. Otherwise, the structure or that concrete cannot last for 100 or 200 of design life. Then these are very important when we are dealing with the structures that they are exposed to the harsh environment. Let's have an example of the modeling. Initiation time of corrosion, as we talked, is again, it's a structure exposed to the marine environment. Then we have chloride diffusion problem here. With the 25 millimeter of the concrete cover, the initiation time will be 4 years. With the 50 millimeter, initiation time will be 23 years, like 4 times more. And with the 75 millimeter, 68 years of the initiation of corrosion, if that specific concrete can be used. It shows that we have like 6 and 17 times more than the 25 millimeters when we have 50 and 75 millimeters of concrete cover. But can it, like, is that a feasible design if we have like 75 millimeter of the cover or not? No, it has to be investigated. But I just want to show that, okay, if we have different like concrete cover, we can achieve different types of the service life. And if we consider the service life as the initiation time and plus corrosion propagation time, then we will have this. This is the corrosion current density. The graph, they shows the corrosion current density. Then with the 25 millimeter, with that specific concrete, the cover will crack after 8 years. And with the 50 after 35 years, and with the 75 after 103 years. Now we are going to the existing structures. We have to inspect and assess the existing structure to understand their current condition in terms of durability, performance, and structural performance, both. Because if we miss one of them, I mean, we will miss the safety of the structure. We should have the preliminary evaluation, which consists of review of plans and available documents if they are available. Visual inspection to detect any defects, deterioration, damage, or distress. And preliminary analysis and condition assessment of the components and the whole structure based on our visual inspection. Then there will be a question, is a structural assessment necessary? If not, then we have to design a proper repair operations or a strengthening, but a strengthening, it cannot be designed before the other stuff. Then only the repair design can be done if we don't need the structural assessment. But if we need a structural assessment, then we have to obtain the actual current properties of the material, mechanical properties of the material. Although some standards, they allow us to use some assumptions for the numbers, but it gives us only some very rough prediction. That's why for achieving the structural condition of the structure, we have to obtain the material properties of the all material and components through the site inspection and some testing. Some of them are non-destructive testing, and maybe destructive testing will be involved as well. After that, when we gather and we collect the data from on-site investigation, we conduct the finite element computer-based modeling. Then the structure will be modeled, and then it will be analyzed, and then the structural assessment will be the outcome of this assessment. And then we can estimate or calculate the load-bearing capacity of this. It can be a bridge, it can be a water treatment plant structures, it can be sewer systems or whatever. I mean, this is the a flow chart, you know, for all kind of a structure. Then when we've got all data and information from the structure, then we will be able to propose a proper, reliable, and sustainable repair operations. Okay, this case study is like for a bridge, 3-span bridge. And you can see the different defects we have: concrete spalling due to corrosion of steel reinforcement and cracks on the abutment of the structure of the bridge. We have deterioration and damage of the wing walls and deterioration of the expansion joint on the deck. And in the right-hand side, the two photos shows the AAR, progress AAR or ASR, progress ASR on the concrete structures. And because the ASR is very interesting types of deterioration, and we talk about ASR a little bit less than the others, that's why I have included a very short video. Yeah, as you can see, the cracks. When we have ASR, we have a network of cracking. Cracks are normally are large cracks in terms of the width, because the ASR starts from internal expansion. Then when we see the cracks, they are a little bit bigger than the other normal cracks. And you can see in the left-hand side, you can see the gel leaching out, and this discoloration of the concrete shows the progress AAR on the structure. You can see the cracks are all over the sorry. Okay, then with the ASR, what has happened? Well, what is happening is we have deterioration and degradation of the concrete matrix, and we will have a structural disintegrity of that component even before corrosion of a steel reinforcement. Then we have to consider this type of deterioration in our design. Okay, then we inspected the structure. Then we have to conduct some testing on the structure. And nowadays, clients, they don't like, or asset owners, they don't like to have this destructive testing on their asset. That's why there have been highly technological achievement in non-destructive testing. Then normally we do concrete cover measure, crack mapping. Crack mapping, I mean, both 3 elements: length, width, and depth. And concrete resistivity measurement, direct one, rebound hammer, and UPV, the combination of duties, which is called SUNREP method, to achieve the compressive strength, or we can achieve the concrete compressive strength and modulus of elasticity directly by using ultrasonic pulse velocity. Then if we need, we do the ultrasonic pulse echo test, which we can achieve the chloride quality in terms of density. We can see the pores in the concrete, voids, cracks, delamination. Even with the UPE, we can understand what has been the problem. Okay, whether the mixed design has been like, there has been like some errors in the mixed design or in the construction practices. When we scan the concrete, we can see the voids. If, for example, if we have like void, like 2 millimeters of diameter of voids in the concrete, or 3 millimeters, then they are based on the construction errors. I mean, maybe lack of proper compaction. We can understand all of them when we assess the concrete. And then corrosion monitoring, measurement of a steel reinforcement. Then this corrosion monitoring, we have different types of electrochemical based corrosion monitoring for the site and field to get the accurate results. The galvanostatic pulse technique is the most reliable and accurate system and monitoring and measurement of corrosion of a steel reinforcement. With the galvanostatic pulse technique, we can achieve corrosion current density, which we can understand the rate of conversion of a steel reinforcement to the rust, and corrosion potential, and concrete electrical resistance. For some investigation, we may need to do the moisture content and carbonation depth. These are the tests which we do like non-destructive, except the carbonation depth. The other ones are non-destructive testing, and they are reliable, but the people who they work with this type of device and equipment, they have to be very skilled, and they could be capable, they can be capable to understand the results which they obtain from the structure.
Okay. Dr. Nabavi, can I ask a few questions from the attendees at the moment?
Yes, please. Yes, please.
Okay. William Ward has a question regarding, when doing an assessment, is it your view that precision of measurement or taking large enough data sets to have a holistic view is more important?
Both of them. We have, for the non-destructive testing, we have to use high quality equipment. Those equipment should be calibrated regularly. And then, yes, the numbers of the tests are important, because for each experimental testing in field or in the laboratory, we have to do the statistical analysis in order to find out our errors involved and the statistical deviation of the numbers. Then, yeah, we have to gain the test and results as much as we can. The higher the numbers, the more accurate the outcome. We can, it's not only, okay, we can do only 3 tests and then we can have like arithmetic mean of them if we can use. I mean, we can use, but it's not the accurate procedure. That's why both of them, the high quality of the equipment and numbers of the tests on site are important.
Yep, and a decent client budget.
Oh, yes. Yes, exactly.
Another question, how are the service life graphs determined for different depths of covers regarding concrete design?
Okay, that one was like concrete design, but I will talk about the existing structure later because we have design life and we have residual service life. Design life, it happens on the design stage, but residual service life is the term which we use for the existing structure. Then we measure the, I will talk about, if please give me some, because it's like a little, we have to cover the other parameters as well. I will mention this, yes.
No worries. And if you don't have the initial design as built documentation, how do you accommodate that lack of knowledge?
Yeah, I mean, it's a common problem. Most of the structures, like with 50 years, 60 years, 70 years, 40 years of age, they don't have even drawings. Then we have to obtain all of those information with the non-destructive testing. For example, the size of the rebar, the arrangement of the rebars, and all of and we have to do the specific site measurement in order to be able to model the structure.
Yeah, so, increases the investigation.
Exactly, yes.
All right, and two questions, hopefully short ones about NDT. Pardon me. What is the best and recommended NDT for crack depth estimation?
Ultrasonic pulse. This is the current slide which I'm going to present is regarding to the crack depth.
Okay, and the other one was about how do you measure moisture content with NDT methods?
Oh yes, we have to do the moisture content test, especially when we want to use like CFR wrapping as the strengthening of the structure. We have to measure the moisture content. We have a special device, digital device, which can measure the moisture content of the concrete. For example, some epoxies coating, they need a specific amount or magnitude of the moisture content, let's say 3% or maximum of 4%. Then we have to measure the moisture content first and then apply the other products and materials. Yeah, we have to.
Okay, thank you.
No worries. Then interesting questions, thank you. The next slide is I have included for the crack depth. As you can see, the same case study, in the right-hand side, the photo of the actual structure, you can see C7 means crack 7, depth 24, C8 depth 57, and then C11 depth is 34 millimeters. What we do, we use the BS 181 part 203 for the measurement of the cracks. Then, as you can see, you can find this method and procedure through the British standard. And in the left-hand side, this is the outcome of the ultrasonic technology, which we use to measure the depth of the cracks. It's important to know the depth of the crack in order to specify and propose a proper repair system. Then, as you can see here, the crack repair is like 24 millimeters, which is in the actual one you can see. And with the ultrasonic test, we can achieve or obtain the quality of the concrete. For example, the left-hand side bottom shows the 3,285 meter per second of the velocity wave velocity, sound velocity. Then it shows us a not very good concrete. I mean, from 2,500 is the less quality, and the upper limit is 4,500 meter per second. Then if we have around 4,500 is a good quality of the concrete, but the 30,000 is like around like a fair quality concrete. And then when we collect all data, for example, this bridge, it didn't have any drawings, it didn't have any documentation. Then we conducted like a very vast and extensive on-site measurement, both geometrical measurement and non-destructive testing. The bridge has 7 precast girders with some cross beams, and the 2 piers with the 3 columns each, and then crosshead or headstock. We modeled this in order to be able to achieve the structural performance of the bridge under the exposed loading based on AS5100. Then this is the outcome of after the loading for different types of the vehicles. You know, you can see the different deflection in our deck. And I have prepared this a very short video for the 23-ton truck, and then we will see for 68-ton. Then we can see the deflection and the effect of the dynamic loading of vehicles with the speed, you know, which we have at that road. This is the like 23-ton, and you can see the deflection, which is acceptable. And this is the investigation on 68-ton truck. Then you can see excessive deflection. Okay, and then we could rate the loading of the or load capacity of the bridge. In the left-hand side, you can see the components, different components, and then we have investigate them or analyze them based for the shear and moment, and then we have different types of live load on the that column. As can be seen in the last one, abutment in shear, it shows that the rating factor less than 1. Then it means that the capacity of that abutment, it is less than it has to be for the bearing of the loading. And that reduction of the rating factor is due to those cracks. You know, those cracks on the abutment which we saw, those cracks reduces the capacity of the concrete under the different loading. Then the shear rating factor is less than 1. Then this abutment has to be strengthened in order to achieve higher loading. And this rating factor is only for 23-ton. If you look at the other vehicles, we have 60-ton, 68-ton, 31-ton, and then we can see, and one of the crosshead shows with the 68-ton, but again less than 1. It means that the 68 cannot pass through that bridge, but 31 can. Then it doesn't need to be strengthened at this stage because the asset owner, they just wanted to have around 44 ton for the capacity of that bridge. Then for achieving 44 ton, then the abutment has to be strengthened because the rating factor is less than 1 for 23 ton of the vehicle. Then it's the very, a summary of the rating factor analysis. And then the repair which we did, we had like damage, which we saw earlier. Then we had to demolish two wings, wing walls completely, and then we designed the new ones, and then we used the drill and epoxy system in order to connect the new concrete and reinforcement to the old concrete. From left to right, you can see that the demolition of the wing wall, and then drill and epoxy of the reinforcement, and then the outcome of new wing walls. And
sorry,
yes.
Dr. Nabavi, there's a couple of more questions that come through.
Oh, yes, please.
With concrete spillways where dewatering is not feasible, which tests are recommended to diagnose internal issues?
Is it a spillway of a dam, I think? Then in dam structures, the defects are a little bit more complex. I mean, we need more like site information, but as a general thought is in water retaining structures like water tanks, dams. I mean, the first deterioration mechanism is the soft water attack. Then the soft water, because the amount of calcium ion in the soft water is very low, then it can dissolve the carbon dioxide available in the concrete. And then after some time, we will see the deterioration of concrete surface, aggregate exposure, and then the matrix around the aggregate, and then aggregate is falling. I mean, this is the consequences of the soft water attack. But the other defects, it depends on the quality of the concrete. I mean, we need to have a little bit more information in order to judge or interpret the test which we have to do, the deterioration mechanism involved with the structure. I mean, I'm not able to, but I mean, the soft water attack, then we have to investigate the corrosion, the concrete quality. I mean, these are the type of the non-destructive or investigation which we have to do. We need more information.
Okay, a couple of questions about the finite element modeling.
Yes.
Which software was used?
We use CSI SAP 2000.
Okay, and how were the cracks modeled in that?
Okay. This is this is like a little bit. I mean, it has come through our investigations and our research and reading that we are able to consider the effects of the cracks on the concrete structure or each components, and then the structure as a whole. Then I think it's a question which I can't. Sorry for that, but I can't have any explanation or detail.
Yeah, there's an element of art to it.
Yes, we have spent more than 10 years in order to find out how the cracks can affect the performance, I mean, the structural performance of that component. Yes.
Okay, thank you.
Graham, finished? Or more questions?
Keep going, thank you.
Okay, no worries. Okay, then the first, I mean, the most important problem with that bridge started with the leaking water through the deck joints from the expansion joints. And because they have used high silicate aggregate, then moisture can accelerate the ASR reactions. I mean, the deterioration rate of ASR can be accelerated by increasing the temperature and increasing or moisture available. Then easily water could penetrate through the expansion joint and reaches to the pipe and crosshead of the bridge, and then deterioration, which we saw. Then they had to be repaired properly. You can see in the right-hand side, two left photo. The first one is like with the grass. It's the joint. I mean, it was the existing expansion joint, and the left-hand side shows the after repair with the cut, the with the like a specific procedure. Then in the right bottom, you can see the crack repair of the abutment. And then after crack repair, the abutment, which we saw, it had to be strengthened. With the top left-hand side, it shows the strengthening of the abutment. The problem with this was the abutment was low in shear. Then the strengthening had to be done with the shear strengthening. With the shear strengthening, we have to, if we use the CFRP wrapping, we have to wrap all around the components, the element, okay? But in this case, we didn't have access to the behind side of the rear side of the abutment. Then we had to have, like, as you can see in the left bottom, very low surface for the strengthening. Then in this case, if we have a strengthen for the shear, then we have to design an anchorage in order to fix the wrap, the CFR wrapping. And you see that our results show that we have to use 4 layers of the CFRP wrap with like 230 gram per square centimeter. Then the photo shows the anchorage. You can see the routing out of the concrete for the anchorage. And based on a standard 10, 12, 24, we have to do the site bonding test before applying the actual CFRP wrapping. And in these photos show the on-site investigation on the bond strength, the tensile bond strength between the CFRP wrapping and concrete substrate. We have to achieve at least 1.5 megapascal of the tensile bonding. Then if it's less than that, we should see, okay, what is the problem? Based on the outcome of the pull-off test, then we can judge whether it's been the bond between the wrap and the concrete, or bond between the lollies and the wrap. I mean, based on the results of the pull-off, we can decide what has been the outcome and what we should do. Then we did the test, it was all right, and then we started wrapping the abutment. And as you can see, the strength, when we have that anchorage in the middle top photo, you can see we have FRP rod inside that anchorage, and inside epoxy, completely covered by epoxy, right hand top side of the photo. It shows the FRP rod, and then it can completely lock the CFRP wrapping into the substrate in order to be not completely fixed. And in the middle bottom one, you can see the finished work of the anchorage system. Okay, then I think the last one is like based on we have questions. I mean, then we have design life and we have residual service life of the structure. Design life is at the design stage, but the residual service life is for existing structure. Then what we do, for example, if the chloride is a dominant deterioration mechanisms, we take some samples, and then in laboratory they can measure the chloride content in increments, let's say with 10 millimeter of increment up to the concrete cover. And if sometimes we do like maybe another like 2 increment after the reinforcement if it's necessary. But within the concrete cover, the chloride content can be measured and then compared with the chloride threshold. And then we can judge, okay, the chloride has diffused, for example, 25 millimeter of the cover, and it's like threshold. Then we have only another 25 millimeter for reaching the chloride to the reinforcement. Then from now, the actual concrete cover has to be considered as 25 millimeter in our mathematical model. I have presented like some of them just for being a little bit more familiar with the mathematical model. Then in all of those mathematical models, we have some parameters in the bottom of the slide. CS, which is the surface chloride concentration, we can measure this one. And chloride threshold is assumption, and I don't have time, but it needs another just one presentation for chloride threshold. And then we have direct measurement of the DC, which is the concrete cover. And then we have the D, which is the chloride diffusion coefficient. Okay, with having those parameters, we can with the mathematical model, we can predict the residual service life of the structure. Or for example, if it's carbonation, we use mathematical model for carbonation, but we have to consider the current carbonation depth. We have to measure the current carbonation depth. Then that depth has to be deducted from the concrete cover in order to find out how much cover, actual cover, remaining for the modeling and residual service life. Okay, then if the corrosion initiated already, you go to the site and you see, okay, the corrosion has already initiated, then measurement of chloride doesn't solve anything, because chloride diffusion modeling is before initiation time. But if we have the corrosion happening, then we have to use corrosion modeling. I have put like 4 of them. Then the service life modeling will be conducted or carried out based on the corrosion parameters, not the chloride diffusion. I mean, we have to very, very careful when the corrosion has started. We have to use corrosion-based modeling. Otherwise, we use like diffusion modeling. Okay. Thank you so much for your attention.
Whoops, I'm sorry. I'll just get my the questions up on the screen here again. In the analytical side, this is one about the, I guess, the modeling, back to the modeling of deflection. Comments been made that ACI has recommendations on how to model the influence of crack depth with structural response, particularly around changing the EI of the member. You can simulate the loss capacity.
Yes.
That's pretty much the basis of your
yes, in some circumstances, yes.
Okay. If there's an independent reviewer's role, which is happening more and more these days, what sort of, you need to be able to provide enough detail for the independent reviewer to carry out that review. Is that the output that is envisaged with these design assessments that you go through?
I didn't quite understand the question. I mean, for the independent, yes. If
somebody's got to carry out.
Yes, for the independent, your third-party review, you mean?
Yes, peer review of the review. Okay,
yes. Yes, I mean, if this, I mean, the inspection has to be carried out. I mean, sometimes with some photos, you know, based on experience, we can find out the problem, but as the third view or third party review, no, we have to do the site visit at least once to understand the problem. Yes, but we do this.
Okay, I guess the question was more, pardon me, a little more towards what the design parameters were that form the basis of the repair.
Oh, yes. Yes, I mean, for the repair or design for a design stage?
Yeah. At the design of the repair, so the carbon fiber strengthening.
Okay, because design for a strengthening design backs to the our analysis on the current condition of the structure. Okay, then I cannot judge about the strengthening design before having all those data which I mentioned, because we have to find out exactly what has happened to the structure, what is the current condition of the structure, what is the current load capacity of the structure, and then based on that we can design the strengthening. I mean, these are related, like, you know, chain together. We cannot select only one chain in order to investigate the whole, you know. Then for the review of a strengthening design, I need the whole information.
Okay.
Yes.
And carbon fiber, a question of cost. It's perceived in some areas as being expensive. Have you done cost comparisons between it and conventional external steel or augmentation?
Okay, I think to specify a method, we have to consider different types of factors. I mean, different factors has to be considered. For example, with the steel, we have the problem is a little bit more labor cost involved, or maybe the transportation as well. But you know, CFR wrap are much fast. I mean, in that regard, better. And the other thing is the design. I mean, life of that material as well. Then steel, if it's a steel, then we have to maintain that steel as well. For example, let's say every 5 years it has to be sandblasting and then paint again in order to prevent the corrosion. I mean, that steel strengthening need to be maintained as well. But the carbon fiber wrapping, for the regional area, rural area, which is not possible to have the crew every 2 years, 5 years to go and maintain the steel strengthening, the CFRP wrap are more reliable at that. And the cost, I think it depends. I mean, we have to consider different types, different factors in order to decide a proper strengthening. So maybe, and sometimes we cannot use wrapping because of that ratio which we have. the carbon fiber wrap or laminate, they can provide up to a certain strength for the structure. And if that ratio is more than the carbon fiber strengthening, then we have to other like conventional or steel strengthening.
Yeah. Just the thought occurred to me with some of these regional bridges being strengthened. What about the impact of bushfire on adhesion or performance of the carbon fibre?
I haven't investigated. I mean, I have not investigated on that regard, but I remember maybe up to 160 degrees should be capable, but I'm not sure. I don't have any number in my mind. Yeah,
no, it was just I guess a thought that occurred. If the aim is to avoid inspections, then brush and whatnot can come up against the abutments fairly easily in a 5 to 10 year period. So it could
yes, I mean, if the fire can reach to any type of structures, we have to do post-fire damage inspection and a structural assessment.
Yep.
And then, yeah, it's
good. Has there been research in Australia about bolting carbon fibre to concrete, or is it always adhered? What other alternate anchoring methods are there?
For strengthening?
Yes, for carbon fibre strengthening.
Okay, carbon fibre strengthening. We have like 3 products for strengthening for the carbon fibre. We have wrapping, which is fabric, and it's like flexible CFRP, and it can be wrapped around the structure, that element. We have carbon fiber laminate, which is not flexible, and laminate is like for shear strength. Strengthening is more suitable than wrap. I mean, if it's like for shear strengthening, we use carbon fiber laminate. But in this case study, which I showed you, we couldn't use because the carbon fiber laminate has to be locked. Itself has to be locked into the concrete. Then we couldn't use the carbon fiber laminate. And the other product is the carbon fiber rod, which you saw. I mean, carbon fiber, CFRP polymer, they can be used instead of steel reinforcement. I mean, they are non-corrodible material. The only thing is because they are relatively new to the market, we don't have any idea about long-term performance of the CFRP rod instead of steel reinforcement. But for strengthening, sometimes we need to use carbon fiber rod. For example, sometimes we have like problem in bending, and then the carbon fiber wrap or laminate cannot achieve the ratio which we want. Then we have to use carbon fiber rod. I mean, yeah, the different scenarios, it has different solutions.
Okay, that's it for the questions. I might hand back over to Kieran.
Thanks, Graham.
Right.
And also would like to thank Dr. Nambavi for taking his time out today to share his knowledge and experience on today's topic.
No worries. Thank you so much for having this opportunity to have this presentation. And I just want to, as a recommendation, please achieve the quantitative parameters as much as you can. You know, we cannot judge about the structure performance based on experience or our visual inspection. Achieve the quantitative parameters as much as you can.
I'm sure everyone's gained a deeper understanding on what's required to carry out detailed condition assessments. If anyone out there does have any further questions later on today or tomorrow, feel free to send them through to ACRA, to our info. Our email is at info@acrasoc.com.au, and we'll make sure Dr. Nambavi has the opportunity to provide a response for those.
I will, definitely I will.
Moving forward, our next presentation is on the 8th of September. Our topic there will be quality inspections for the remediation of corroded structures, and this is going to be presented by Justin Rigby. And as per our other webinars, this is free to all of our members. Another reminder that our AGM is being held on Thursday, 8th of October, via Zoom from 4:30 p.m. That is open to all of our members. And keep up to date with everything ACRA. Keep an eye on our social media, your inbox, or of course our ACRA website, which is www.acrasoc.com.au. And finally, thanks again, everybody, for your time, and we'll see you at our next event.
Thank you.